Alright, today we're really going to look at what Extension 2 is all about and how it is separate from our work with motion in Extension 1. Today we're looking at the idea of resisted motion. So in real life situations we need to consider resistance. Now this is where the fluid or gas or liquid the particle travels through or the surface it travels over provides a resistance to the motion. Now resistance is a force, not acceleration. Since the resistance increases as the velocity increases, acceleration is a function of velocity. Okay. Little flowchart here that's going to help us work with these questions. So you think you've got something going through a medium and it's being resisted, usually air resistance, or maybe it's some sort of fluid resisting its motion. We've seen this before. The result involves displacement and velocity. We're going to sub v to v dx. If it involves time and velocity, we're going to sub to v to t, and if it involves time and displacement, we're going to sub to v to t, but then we're going to have to flip it, integrate again. Okay. Every question will give us a simplified equation of motion to use, or enough information to create one. The resultant force is the force propelling the object in the direct positive direction, plus a resistive force which acts in the opposite direction. So we've got linear drag, which is where it will say resistance is proportional to velocity. So the normal force of the object would be mx double dot. When I say normal, I don't mean the literal normal thing on an inclined plane. I just mean what it normally would be. That's normally what the force would be, but we're taking off some sort of resistance. It's resisting the movement. Now, quadratic drag is something that's quite easy in one dimension, not so easy in two dimensions, but in one dimension, it's just telling me, hey, the resistance is proportional to the square of the velocity. So here again, this would be our normal force, but we're taking off some sort of resistance. Okay. Some tricks for success here. So these questions can be quite tricky if you overcomplicate it. So you really got to make sure, number one, if the object is not being pushed, and this is mainly introducing these because when I was doing these questions, these were the things that I wrote down could be common mistakes, and some of them are mistakes that I made. So if an object is not being pushed, then it only has a resistive force acting upon it. So I've got this question here. We've got an object is moving horizontally in a straight line. It doesn't say anywhere that it has a force moving it. Maybe I've just thrown it, maybe I've thrown it on ice and it's moving along the ice, but there's no force pushing it along the ice. The only reason it's moving is because it has velocity, but there's no force that is maintaining it moving forward. It's going to eventually slow down. So the only force acting upon it is its resistance force. So in the first step of this question, we would say that the force is just the negative resistance. We're told there is a resistance here, not this. The question doesn't mention a forward force. There's no force moving it forward. The object is not a rocket. It doesn't have anything pushing it forward. Next, we're going to read the question very carefully. If the question mentions a resistive force, for example, kV squared, then this force as constant already has m factored into it. So we know F is equal to ma, and if it says resistive force is kV squared, then this k already has m factored into it. We're not going to multiply it by m. Another reason we don't do that is because resistance is independent of mass. Now, as you're working through this exercise, there's going to be some things that might be a bit strange. If we see it experiences air resistance, we're going to start with x double dot and not mx double dot, as opposed to it saying resistive force. Now, if it says resistance is proportional to velocity, then it's helpful to multiply it by m if it doesn't mention the word force. So for example, x double dot is mg minus mkv. Now this is not necessary. In fact, it is wrong to do that because resistance is independent of mass. But it does make our calculations easier. Now in the HSC, they're not going to introduce this ambiguity. They're going to make it very plain what they want you to do. So generally we're not going to do this, but sometimes putting this M here makes our calculations easier. So why is that allowed? Why can we do something that's wrong? Well, it's not really wrong. Let's say we had mx double dot is mg minus alpha v. If we wanted to know its acceleration, we could divide everything by m, and we're going to get g minus alpha m on v. We could say, okay, let k equal alpha on m, and then we just got this. But if we initially had an m here, and we just divide by m, and we get to this same thing. Now you might be thinking, oh, this k is not the same as that k, and it's not. But these are just random constants. We don't care what they are. They're just constants, like when we integrate a constant, we don't have to multiply it by 2, for example. So this m, we can put it here, it makes our lives easier. Now you can do questions, and if you don't put the m there, you will get an answer that looks different. But when you actually analyze it, it's actually the same thing. You're just constant k means something different. Okay. On that, please, if they give you questions and they have already defined x double dot, do not prove them. It says do not prove them, but don't even try, because you will get the question wrong, and that's because the constant k that they've decided has already factored in the division by m, and if you try and prove it again, your constant k is going to be different. Okay. So questions involving displacement and velocity. In this lesson, I should have mentioned we're looking at horizontal resisted motion. So we've got a car of mass 50 kilos is being pushed along a horizontal path with force 200 newtons. We're going to start our force equation. So mx double dot, which is F equals ma, it's some 200 newtons force in the positive direction, but friction is a frictional force is acting against the car's motion, which is proportional to the square of the cart's velocity. So minus kv squared. Now we know the mass is 50 kilos. So 50 x double dot is 200 minus kv squared. Divide both sides by 50. 50 is equal to 200 divided 50 is 4 minus kv squared on 50. Done. Part 2. Show that the velocity of the cart, given it started from rest, is given by that. Okay. Now we want something involving velocity and x. We want x to be the subject. This is where we're going to be using v to v dx. So we're saying v to v dx. We haven't used that one in many examples. V to v dx is 4 minus kv squared on 50. This one's going to be a lot more commonly used in resistive motion. The next thing we're going to do is I might make this a single fraction. Or actually what we might do first is we're going to divide both sides by v. So d v dx is equal to 4 on v minus kv on 50. We might now make it a single fraction. So we're going to have 200 minus kv squared on 50v. And we want x to be the subject. So we're actually going to have to flip this upside down, and we're going to find dx to v. That's going to be 50v on 200 minus kv squared. And we're going to have a go at integrating this. Oh. All right, we might take out a factor of 50. So this is 50 times by v on 200 minus kv squared. Now this is, it's looking like it's in the form of the natural logarithm. We might say dx is here and dv is here. But ideally on the top we would want 2v. So we need to put a 2 down here. So 25. And actually, since there's a k here, if we differentiate kv squared, we get 2 kv. So we really want a 2k here, which means we need to put a k here. Okay, So if we integrate this, we're going to integrate, so x is equal to, integrate. 50 on 2k is the same as 25 on k, ln of 200 minus kv squared plus c. Now you can, if you want to, practice doing this as a definite integral. We know that we are starting from x is 0. We're assuming so. It doesn't say anything else. Usually with these questions, we're going to assume that the starting point is 0. And it doesn't really matter because we're not moving along, say, a Cartesian plane. We're actually physically, tangibly somewhere. So we can just set the starting point to be 0. And we're integrating to x. Let's just have a go finding the constant c. We haven't done that for a while. We know that its velocity is initially 0, I think. Does it start at rest? Given it started from rest. So that means v0 is equal to 0. So its initial velocity is 0 and its initial displacement is 0. So 0 is equal to 25 on k. And actually, we need to actually put a negative here because if you integrate this, you get negative ln. So minus 25 on k, ln of 200 plus c. Now that means c is equal to positive 25 on k, ln of 200. So therefore x is equal to 25 on k, this is my c value here, ln of 200, minus 25 on k, ln of 200 minus kv squared. Using our basic log laws, we can see that this is going to become 25 on k, ln of 200 on 200 minus kv squared, which is what we're after. Okay, questions involving time and velocity. So generally we're going to replace acceleration with d to t. So a car of mass 2,000 kilos starts at rest and travels along a horizontal road. The engine produces a constant force of 6,000 newtons, while a force of 40 newtons oppose the motion of the car. So mx double dot, 2,000 kilos x double dot, is equal to the engine force of 6,000 newtons minus some sort of resistive force. We're told that this is a resistive, a force is opposing it, so we're taking it away. Okay, let's divide both sides by 2,000, so x double dot, what, 6,000 divided by 2,000 is 3, minus 40 on 2,000 is 1 on 50, so v on 50. Multiply up, get a common denominator, we're going to get 150 minus v on 50. And x double dot is another way of saying d to t. Okay, done. Now we want to prove that velocity is something involving time. Now we can't integrate this at the moment because there's velocity here and t down here. So we're going to have to flip it upside down to do this. So dt is equal to dv, and that's on dv is 1 of 50 on 150 minus v. That's nice and easy to integrate. We've got t is equal to minus 50 ln of 150 minus v plus c. Now let's have a look at our initial information to find c. We're told it initially at rest, and we're going to assume, well, initial means time is 0, so the velocity is 0 when time is 0. So 0 is equal to minus 50 ln of 150 minus v plus c. Well, the v is 0 in this instance because we're starting at 0. So t equals 0, v equals 0 because it starts at rest. So c is equal to 50 ln of 150. And in another page. So therefore, using just putting in our plus c and using some log laws, obviously we're going to get 50 ln of, what did we say, that was 150? So 150 on 150 minus v. We then might, let's have a look at where we're after. I think we want v to be the subject. Yep. So Might divide both sides by 50, raise it to the power of e. So 150, we've got 150 minus v is equal to e to the t on 50. Let's times everything over. So we're going to get 150 is equal to 150 e to the t on 50 minus v e to the t on 50. Plus that over minus that over, we're going to get velocity is equal to e to the minus t on 50 by dividing it over is equal to 150 e to the t on 50 minus 150. We might multiply through the e to the t on 50 and take out a factor of 150, so it's going to be 150. If we multiply that with that, we get 1 minus e to the minus t on 50. And I think that's what we're after. Let's have a look. Beautiful, nice and easy. Okay, the next example we're going to have a look at some more resisted motion. So we've got a supercar has a mass of 500 kilograms and its engine generates a force of 1,000 newtons. Its motion is opposed by a resistive force of v squared on 10. Before we actually answer any of the questions, let's have a go at forming our equation of motion using Newton's second law. So we know that mx double dot is equal to, we've got our driving force, the engine force of 1,000 newtons, and we're subtracting the resistive force. Now we know that the supercar has a mass of 500 kilograms, so this is 1,000 minus the resistive force of v squared on 10. And we've got x double dot there. We divide both sides by 500, we're going to get 2 minus v squared on 10 times 500, which is 5,000. Okay, now part A says what is the maximum possible speed? Now, maximum possible speed, or its terminal velocity, obviously is as fast as the car can go. Now we think, okay, acceleration means that your speed is increasing over time, and if I'm at my maximum speed, well, I'm not accelerating anymore. My acceleration is going to be 0. So if we set the acceleration to be 0, and we solve that equation, we're going to get v is 100 meters per second. Now it is going to be meters per second. It should, I feel like, be a bit more specific. In the question it doesn't really specify, but scientific units in newtons. Now newtons and acceleration are in meters per second. Newtons is another name for a force. I think it's kilos per meters per second or something funny like that. Kilos per meters per second, yeah, that's what it is. Kilos per meters per second. And that, instead of writing that every time, they just named it newtons. So it is going to be meters per second, which is about 300 or exactly 360 kilometers per hour. Think about your question logically. Does it make sense for it to be kilometers? A maximum velocity of 100 kilometers an hour for a supercar is too small. Part B says if the car starts from rest, prove that the time taken to read that speed is equal to this. Now we've already decided that the equation for acceleration is 2 minus v squared on 5,000. If we have a go, let's make that 10,000 minus v squared on 5,000. Now we want time and velocity, so we're thinking dv to t, but to do that we need to flip it upside down. So we need to say dt to v is equal to 5,000 on 10,000 minus v squared. And we need to integrate that. So we need to find the integral of dt, which is going to be equal to the integral of 5,000 on 10,000 minus v squared to v. Whoever thought you wouldn't use partial fractions in the real world, we're going to have to do it here. 5,000 integral, if that's a difference of 2 squared, it's going to be 100 plus v, 100 minus v. Now let's just use our cover-up method. So we need to put in minus 100 here, so it's going to be 5,000 on 100 minus 100, so on 200. So that's going to be 25 there. Oh, sorry, and if I do it that way, I haven't pulled out a factor of 5,000, so I'm going to leave that there. And then we're going to put in minus 100, so it's going to be 5,000 on, sorry, we're putting in a positive 100 now, so 5,000 over 100 plus 100, which is on 200. So they're both going to be plus 25. So if we have a go at integrating that with respect to v, we're going to get the t is equal to 25 ln of 100 plus v minus that negative there, minus 25 ln of 100 minus v plus c. Now we know that it initially starts at rest. Now I might just combine this ln first, so this is going to be 100 plus v on 100 minus v plus c. Now we know when t is equal to 0, the velocity is equal to 0. We're just going to say that means c is equal to 0. That's pretty obvious why. That's going to be 0, that's 0, and 100 over 100 is 1, and ln of 1 is 0. It's very obvious. So therefore t is equal to 25 ln of 100 plus v on 100 minus v. Okay. And that's what we were trying to prove, so we're done. Okay, thank you. Okay. The next example is questions involving time and displacement, and these are going to be usually the most involved questions because they involve 2 steps of integration. So have a read of that question. We've got a particle travelling, initial speed u, and we're experiencing some sort of resistive force that's stopping my motion. Now importantly, our object, it's travelling forward, but there's nothing pushing its motion forward. It's just travelling at a speed. It's not a rocket, there's no force pushing it. It's just moving and it's going to be slowing down. Now we know the resistive force has this magnitude here, and it's negative because it's slowing something down, and it's a resistive force. So here we can cancel these, and we've got x double dot is equal to minus 2 plus v. Now we want to have something that involves x's and times, which means I want something that involves time, and the only thing that involves time that also means acceleration is v to t. But to solve this, we do need to flip it upside down. So 1 on, we've got minus there, 2 plus v. Now that's obviously going to give us minus ln of 2 plus v plus c is equal to time. Now we know when time is 0, its speed is u. We're told that in the question. Which means c is positive ln of 2 plus u. Subbing that in and applying some of our log laws, we're going to get t, time, is equal to ln of 2 plus u over 2 plus v. Okay, but the question wants something that involves x and time. And to integrate this to use something that involves x's, we need to make velocity the subject. So let's raise everything to the power of e. That's going to be e to the t. So 2 plus u is equal to 2e to the t plus v e to the t. Okay. So the next step is we need to make v e to the t the subject. So v e to the t is going to equal, subtract everything over, we're going to get 2 plus u minus 2e to the t. Divide the e to the t over there. It is going to cancel in some instances, so e to the minus t plus ue to the minus t. And it's going to cancel here. The reason this has become minus e is because 1 over e to the t is e to the minus t. Now velocity is just dx to t, so dx to t is equal to 2e to the minus t plus ue to the minus t minus 2. Just integrate that. X is equal to minus 2e to the minus t minus ue to the minus t minus 2t plus c. Now we know when t equals 0, x is 0, it starts at origin at rest. So 0 is equal to minus 2 minus u plus c, or plus 0 plus c. So c is equal to 2 plus u. So therefore x is equal to minus 2 e to the minus t minus u e to the minus t minus 2t plus 2 plus u. Now, if we have a look at what we were trying to prove, we were trying to prove u plus 2, 1 minus e to the minus t minus 2t. If we have a go at expanding that, we're going to get u minus u e to the minus t plus 2 minus 2e to the minus t minus 2t. Now we have a look. Yep, that's the same thing. Done. All right, thank you.